background some noise is there.
Okay, fine. I'll take care of that. Better?
Yes, sir.
Yeah. Okay, so yesterday's question. From what I have seen, none of you got it right. What I was trying to convey, none of you could actually get the point. See, let me share the screen of my worksheet. See, we had this problem of uniform beam fixed at supports and subjected to uniformly distributed load Q. It required AE as well, and this is the origin and this is X, this is Y. And this is 3. Right? So, the problem was develop a finite element model for the analysis of this beam, fixed beam, uniform fixed beam. Now, obviously, all of you know that we have derived this Euler-Bernoulli beam for uniform distribution for whatever length and EI. If this is the node I, this is node J, then there are Vi and theta I, Vj and theta j. These are the degrees of freedom, and stiffness matrix is naturally given by what is this? So Y by L cube, 12Vi by L cube, then this will be 6EI by L square, 6EI by L square, and similarly there would be if this point rotates by positive angle, this is going to be 6EI by L square, 6EI by L square, and this is 4EI by L, 2EI. Yeah. Okay, so let me just correct this figure corresponding to VI, degree of freedom, unit displacement for VI, right? These are the moments that you can, moments and shear force that you can relate to from your basic mechanics of structural mechanics problem understanding, right? So sinking of supports, 1 degree of freedom VI, if I impose unit displacement to VI, and all other degrees of freedom, I mean theta I, Vj and theta j, they are restrained to zero, so these are the forces that are acting, right? And that becomes the stiffness coefficients of this first column, right? So you have stiffness coefficients of first column as minus 12Vi by L cube, and then theta I minus 6EI by L square, and Vj 12Vi by L cube, and minus 6EI by L square. And similarly for unit rotation at theta I and all other degrees of freedom restrained to zero, you get these forces. So these are the relations that you probably recall from slope deflection equations. So you have 6EI by L square, 4EI by L, 6EI by L square, and 2EI by L. Right? So some sign convention is getting mixed up. So nevertheless, you can fix it out. Just look at the forces correctly. What are the, maybe I got the senses of the forces wrong. But the idea is, you have, when you have this element, you already know its stiffness matrix. We already demonstrated that the stiffness matrix of the beam element is same as what you obtain from the stiffness in the matrix methods of analysis. So that was settled, and you could have straight away started from this point that beam element would be a C1 element of two nodes with 2 degrees of freedom at each node, Vi theta I and Vj theta j. Now the question that I wanted to address was, how are you going to model this problem? Now if I model this problem by one element only, say if I just say use this entire length of the beam and model it as a single element, what happens? So let me just say KE BE is equal to FE plus QE. QE, these are the internal stress resultants. So if you model the entire problem by just one element, and this is Q, right? So this Q will be replaced by, and we have degrees of freedom V1 theta 1, V2 theta 2. These are the 2 degrees of freedom, and this is node 1, node 2, and this is element 1. So the stiffness matrix, whatever we have, that remains one element stiffness matrix, no assembly required, that is the complete structural stiffness, multiplied by whatever the degrees of freedom are, V1 theta 1, V2 theta 2, etc. is equal to the forces. What will be the forces? Forces are going to be QL by 2, QL by 2, and this is going to be QL square by 12, QL square by 12. Right? So the forces are going to be QL by 2, and then this is in the positive sense, QL square by 12, then QL by 2, and then this is in the negative sense, QL square by 12 minus QL square by 12, plus whatever the stress resultants are, V1, M1, V2, M2. These are the stress resultants, internal stress resultants. Now, what I wanted to convey to you is the importance of finite element modeling or discretization, the development of the mesh. As it is, the finite element modeling is complete if you just model the entire structure by entire beam by just one element. Nothing wrong with that. You can very well do that. But what happens now is something very, very interesting. What are the boundary conditions of the problem? Any ideas?
So slope and displacement both the nodes are 0.
Exactly. So all the degrees of freedom of this problem are the deflection at the 2 nodes V1 and V2, and slope at 2 nodes theta 1, theta 2. These are the only degrees of freedom. And if I impose all of them to be 0, these are the boundary conditions, then we had The displacement approximation is V1 n1x plus theta 1 n2x plus V2 n3x plus theta 2 n4x. Now if V1 is 0, theta 1 is 0, V2 is 0, theta 2 is 0, then obviously V hat x is equal to 0 for V1 is equal to V2 is equal to 0 and theta 1, theta 2 is equal to 0. So what does that mean? No matter what intensity of load you apply, your finite element model is going to predict the displacement of the beam as 0. Technically, you have not done anything wrong, and still your answer couldn't be more wrong. Is it sinking in?
Yes, sir. This is because of the boundary conditions.
No, this is not because of the boundary conditions. Boundary conditions are what they are. You cannot argue about boundary conditions. Those are the that is the input of the problem. Part of the problem definition. Whatever boundary conditions are there, you have to impose them. Otherwise, you will not be solving the problem which are specified. You will be solving something else. The problem is inadequate refinement of the mesh, or you are using what we call as too coarse a mesh. Your problem will be solved if you use two elements to model one span. If I instead model this problem